Welcome to today's tutorial. Let's get started. Here is our agenda for today. We're going to talk about built-in high-speed output functions, including PWM and frequency. We'll also talk about setpoint controlled outputs. Then we're going to talk about the HE-XH-SQ option card. We'll look at application examples and we will have video demonstrations throughout. As always, we will finish with a Q&A session. Here is a list of the Horner OCS products that support high-speed outputs. Typically, there is about 2 high-speed outputs per OCS model. In the micro OCS, all models including the relay output model support high-speed outputs. The XLE and XLT supports high-speed outputs for the models 3 through 6. The X5 also supports high-speed outputs. The XL series OCS supports high-speed outputs for models 3 through 6. If you're using the Model 2, which is the relay version, you can add the HE-XH-SQ option card to your system, and that will add the capability for high-speed outputs. The products that do not support high-speed outputs is primarily the RCC family, with the exception of the RCC 6512. Let's start with PWM. A PWM output is a DC square wave signal at a fixed frequency, let's say 1000 Hz or 10,000 Hz, where the duty cycle will vary from 0 to 100%. For example, if you have a pulse with a total period length of 50 milliseconds and the pulse is on for half that time, say 25 milliseconds, your duty cycle would be 50%. Functionally, a PWM output can act similarly to how an analog output looks. Typically, an analog signal sends an output, and through that output the device that receives that signal can effectively scale it and replicate an integer value, for example. The PWM is similar, but instead we have a pulse train where the receiving device is measuring the duty cycle of that signal, and then replicating an integer based on where that duty cycle is between 0 and 100%. Now let's talk about a frequency output. This is very similar, but instead you're going to typically fix your duty cycle at 50%. So the pulses are on for half the time and off for half the time at a given frequency, but you're also going to vary your frequency. For example, instead of your frequency being fixed at 1000 Hz, your frequency varies from 0 to 1000 Hz. Then the receiving device effectively measures the frequency and based on that replicates an integer value. Again, functionally, this is very like an analog output signal would act. Now let's talk about how to configure in the OCS a PWM or frequency output. We need to go to the local I/O tab because this is an I/O configuration type function. We'll go into module configuration and then to the digital output or PWM section. We can configure our output type for Q1 and Q2. When configuring them for frequency or PWM, we're going to select the radio button for PWM. Then we can use registers assigned to the high-speed output functions for duty cycle and frequency. By manipulating those AQ registers for frequency and duty cycle, we can either fix the frequency and vary the duty cycle, or we can fix the duty cycle and vary the frequency. Once we have finished our hardware configuration, we can do our programming. Here are the specific analog output registers that are tied to the duty cycle and frequency for either output 1 or output 2, depending on which one we're using. Then we can manipulate those registers to replicate our PWM or frequency output. For example, let's say you want to manipulate your duty cycle value. The way the scaling works in the OCS is that the duty cycle register is scaled to 32,000. For a 50% duty cycle, set the duty cycle register to 16,000, which is 50% of 32,000. Now let's look at the frequency. The frequency register is set in Hertz. If you want to output 1000 Hertz, you simply set it to 1000. Here's a note on the high-speed memory map. Whenever you're working with a high-speed counter or high-speed outputs, you need to know which I/O registers are being used by the high-speed output function or the high-speed input function. You can find this in the user manual for your particular OCS, all of which can be found under product documentation on the Horner website. Another note is that the XL series models 4 and up can be used in both 2-channel and 4-channel mode. By default, they're typically in 2-channel high-speed counter mode. If you want to use them in 4-channel high-speed counter mode, you need to do a firmware update to your unit to support that. That firmware update is changing out the 2-channel FPGA file for a 4-channel FPGA file. If you're not sure what mode your OCS is running under, you can go to the System menu under Status, scroll down, and you can see the channel mode. Now we'll look at finding the maximum frequency that is supported by the OCS that you're using. You will find different specifications in your cut sheets for specific models. The Micro OCS family can support output frequencies up to 65 kHz, meaning they were built with output chips that can support up to 65 kHz as standard. For the XL series, models 3, 4 and 5 can only support up to 5 kHz. In many applications, that's plenty, as you may only need a PWM signal up to 1 kHz or a frequency signal at 5 kHz or lower. However, 3, 4 and 5 have output drivers for those I/O versions that can support anything faster than 5 kHz. The Model 6 for the XL series can support up to 500 kHz, as it has newer output drivers that can handle those higher speeds. For those using the XL series, if you need to go faster than what your maximum speed allows, you can add a high-speed option card to your system, which fits under the back cover. You can also use this card to add high-speed output capability to the relay model for the XL series, which is the Model 2. You can't use a relay as a high-speed output, but by adding the HE-XHSQ card, even if you're using relay outputs, those two high-speed outputs, which can have much faster high-speed output capability, can be used for the two high-speed outputs in the system. If you're using it for the models 3 through 5, then you'll get faster frequencies than what you would get with the built-in I/O. If you need a PWM signal or a frequency signal at 5 volts, remember 24 volts is the standard voltage for the high-speed outputs, then adding the HE-XHSQ card to your system can give you 5 volt outputs. 200 kHz is available as the maximum frequency for the standard HE-XHSQ card, and 2 MHz is the output frequency available for the HSQ5 5 volt output version. Next, we're going to do a demo of frequency output and of PWM output. The first thing we have to do is go through the Seascape configuration process. Then we will assign variables for the duty cycle and the frequency. Finally, we will tie those variables of duty cycles and frequency to the specific analog output registers that are allocated for that high-speed output. For high-speed output number 1 on an XL7 I'm going to be using for my demonstration, I went to the user manual and found the chapter on high-speed inputs and outputs. I found that my duty cycle and frequency registers for output number 1 is AQ421 and 423, and the registers for output number 2 are AQ431 and 433. Let's begin our demonstration. We'll go into Seascape, and then let's start the I/O configuration. I'll go into local I/O under the configuration button, then module setup. Then I'm going to go into digital output / PWM. First step is to configure output number 2 for PWM / high speed counting. I'm going to configure PWM as my option for output 2, which is already set. That's all the configuration that's required for PWM and frequency output. The next step is I need to create variables for my duty cycle and frequency, which I've done already. I have a variable here called HSQ2 duty cycle and HSQ2 frequency, which are double integer values that are unsigned. They need to be tied to the specific analog output registers allocated for that function on my XL7. Again, AQ431 and 433 are the analog output registers for duty cycle and frequency for high-speed output number 2. Now let's look at my XL7 that's running this program. I have my I/O simulator here. Remember, we're looking at output number 2, or Q2. We are going to be watching this LED number 2, which is wired up to Q2. First, let's set our duty cycle, which is scaled to 32,000 counts. I want a 50% duty cycle, so I'll set this to 16,000. Next, I need to set my frequency. We want to see the frequency results, so I'll set it to something low that our eyes can easily see. For example, 1 Hz. Now, output number 2 is flashing at a 1 Hz rate. Now let's modify the frequency. I'll set it to 2 Hz, and you can see it changes and flashes faster. Now let's try 5 Hz, and I would guess that we can probably see flashing up to about 10 Hz with our naked eye. Anything faster than that is probably going to be difficult to detect that it's flashing, and it will just look like it's on continuously. Now let's show a PWM demonstration. I will make some changes here to show you the duty cycle. I'll change my frequency to 1 Hz, and let's start varying our duty cycle. Actually, let's set it to 1000 Hz. Now it just looks like that output is on continuously. When looking at an LED output, varying the duty cycle varies the perceived brightness of the LED. If I set my duty cycle down to a low value, let's say 4000, we should notice the brightness of that LED going down considerably. You can see the perceived brightness of the LED went down. And then if I set it to a high value, like 30,000, you should be able to see that the LED gets considerably brighter. That's because the voltage is on for a much larger percentage of the time at 30,000 than it is at 1000. This is an example of a PWM application where we fix the frequency and we vary the duty cycle. Next, let's look at a setpoint controlled output. What are setpoint controlled outputs? This is a mode in which the OCS high-speed outputs can be turned on or off independent of ladder scan. The point where they're turned on and off is tied to a high-speed counter accumulator setpoint. An example might be using a high-speed counter connected to an encoder where the encoder is telling us a particular position or the position of a machine or an apparatus. Then we may decide that we want to turn an output on precisely at 30,000 counts and precisely off at 31,000 counts. We can accomplish that by using a setpoint controlled output. Normally, when we turn an output on or off manually in our ladder scan, the point at which we turn that output on could be 5 or 10 milliseconds from when we actually reach that total in our high-speed counter. Whereas if we use a setpoint controlled output, the output is going to turn on exactly at or microseconds from the time we reach that particular value. Let's look at how to configure that. We would go back into our local I/O tab, go back to the output configuration, and then select HSC output as our radio button for that function. For the XL series, to configure whether the output turns on or off, or toggles based on achieving the high-speed counter accumulator setpoint, we have to leave the high-speed output dialog and go to the high-speed counter input dialog. At the very bottom of that, we can configure what we want our match to be. So when we have a match configured to turn the high-speed output on, do you want to turn it off or to toggle? For the micro OCS, you don't have to go to the high-speed input section to configure the match type. You can do it from the high-speed output configuration dialog with a pull down that gives you those same choices. It also gives you an additional choice of generating a pulse of a particular width based on that function. Once you've done your configuration, the next step again is to look for the analog output match values for your particular OCS. For the XL series, you have 2 match values per output that you can configure or access, but you don't have to use them both. For the micro series, you only have 1 match value. Another thing you'll want to do in your program is find the Q bit that's been assigned so you can manually reset the output. For instance, if you've set your match to on whenever your accumulator reaches a present point that's in the match 1 value, you're going to turn the output on. To turn that off, you use one of the Qs that's assigned to that function. By turning on that Q in your program, you can reset the output that was turned on through the match function. Another thing you may want to do is to find the %I bit that has been assigned so that you can monitor the state of the high-speed output. You won't actually use the Q1 or Q2 bit, for instance, to see whether that match has happened, and instead you're going to use an assigned %I bit. Again, you can find this information in the chapter of your user manual for your particular OCS that covers the high-speed I/O. Let's do a demonstration for the setpoint control output. We're going to start with the configuration again. Next, we're going to assign our variables, but in this case, I want to assign variables for my match values. I want to assign variables from my output reset so I can clear that high-speed output after I set it to a match function. And I also want to assign a variable so I can monitor the current status of that match value. I'm also going to find the accumulator value for the high-speed counter I'm using so I can monitor that on the screen as well. Once I have found those AI, AQ and INQ values for my high-speed output, Then I'm going to make sure that those are all mapped to the variables I've created. Now let's go ahead and demonstrate all that in Seascape. Let's start with configuration. I'll go to the local I/O, back to the I/O configuration, and then module setup. Again, we start with the high-speed output. Now I'm going to be working with high-speed output number 1 as a setpoint controlled output. I have set it for HSC1 output. Because I'm working with an XL7, to set my match type, I need to go into the high-speed counter configuration and set my match. I have it set for on at the moment. You may notice I'm using a quadrature, so I have an encoder connected up and I'm using the encoder built into my I/O simulator. That is the configuration complete. The next step is to find the real-world I, Q, AI and AQ values in my user manual and assign those to the variables. Here are my variables. The first is the high-speed counter number 1 accumulator. That's tied to AI 401. I've also assigned the clear bit so I can go ahead and clear that accumulator when I need to. That is tied to Q1603. I have created variables for my 2 available match values and I've mapped them to the appropriate AQ values. Now I have my output state that I can monitor. That will tell me if my high-speed setpoint controlled output is on or off. Then I have a bit that I can use to reset that high-speed output. Let's look at the XL7 screen. Then our setpoint controlled output. This time we're looking at output number 1. Currently my accumulator is set at 0 and my output is set to turn on whenever the accumulator reaches 100. I will manually change my accumulator here by using my built-in encoder. Now you can see my high-speed output has turned on the output number 1 LED. I also have my indicator here that's tied to the %I bit that shows the indication status. Now I'm going to reset that output using that button, and that's doing it in the ladder scan. Now when I reach 300, we should see the output turn on again, and this is because I'm in turn on mode. We've reached 300 and the output turned on again, and I can reset it. Let's look at toggle mode next. I'm going to go back to Seascape and actually change my configuration to toggle mode instead of on mode for my match style. Okay, so back into configuration. I'll go to my local I/O config module setup and then set my match mode. I have to do that in the high speed counter config, so I'm going to change it from on to toggle. Now I will go back out of my configuration and then we need to re-download this program. Now it's going to give me a warning telling me that I'm changing my I/O configuration, and since I'm talking to Ethernet, that is a potential problem. It gives me this warning, but that's okay because I didn't change my Ethernet configuration. So now Seascape is changing the match mode for my high-speed setpoint controlled output function. We've completed the download, so we'll go back to our overhead view and then go back to our setpoint controlled output. We still have our match value set for 100. That's match number 1, and match number 2 is set to 300. Let's see what happens when we start changing our encoder value when we get to 100. As you can see, the LED turns on. Now let's see what happens when we get to 300, and you can see it turns off. In toggle mode, it alternates between on and off with the match set points. Thank you for joining us for today's tutorial. The Q&A session will begin shortly.
Everybody, hope that was clear and gave some food for thought on use of high-speed outputs on the OCS. Got some questions coming in. Can I use the high-speed counter inputs for an HDL encoder and use the high-speed outputs with the HSC functionality in the same program? Yes, you can. Basically, the high-speed operation is all handled on a separate chip within the OCS, so it doesn't load up the processor in the unit. It doesn't slow your scan time down or anything. It's all handled through logic, and the blocks are all completely independent in terms of the functionality. So use of one with anything, you know, and any combination of HSC functionality and PWM functionality all works fine together. Okay. So let's have a look at upcoming webinars. So what have we got coming up? Well, obviously we've just seen the high-speed outputs on the 24th of the 2nd. We've got using trends coming up on the 3rd of the 3rd. Data parsing instructions in Seascape on the 10th of the 3rd. This is looking at logic for handling data streams and building output messages and parsing input messages for situations such as using a serial port to talk to a barcode scanner, that kind of thing. And then on the 17th of March, there is no webinar. We've got a bank holiday in Ireland, St. Patrick's Day. And then finally, or not finally, but the last scheduled webinar at the moment is on the 24th of March on analog filtering techniques. And we're busy at the moment working on the schedule for April and May. I would imagine that will be online available for you to see in the webinar next week. So thank you very much for attending, everybody, and we'll hopefully see you at next week's webinar. Thanks very much.